the temperature in degrees Fahrenheit is going to be given by capital T. So T is temperature in these kinds of problems. And also, lowercase t is going to be time. So it depends on whether it's capital or lowercase, whether I'm talking about temperature or time. And I've got a function that will tell me the temperature of this coffee after a certain amount of time has passed. The first question says, what was the temperature of the coffee when it was first poured into the cup? So I'm looking for temperature. I'm looking for capital T. And based on this function, it seems like I should be given what is lowercase t? 0. If I just poured the coffee into the cup, 0 minutes have passed. And then the formula for temperature is 45 plus 140 times e to the power negative 0.05 times 0. Negative 0.05 times 0 is just 0. E to the power 0 is 1, because anything raised to the power 0 is 1. And then 45 plus 140 is 185. So I can tell that the coffee started off at 185 degrees Fahrenheit. First poured. What was the temperature of the coffee after 20 minutes? So again, I'm looking for temperature, capital T. This time, lowercase t is 20. So again, using my formula, temperature is going to be 45 plus 140 times e raised to the power negative 0.05 times 20. That's the same as negative 1. And what do you get if you type in 45 plus 140 times e to the negative 1? Okay. 96.5 degrees Fahrenheit. So again, it's a warm object, so the heat is flowing from the warm coffee to the cold outside environment, and it's lowering the temperature of the coffee over time as it loses heat. So after 20 minutes, it's only 96.5 degrees. What was the temperature outside? So this is a funny question. We know that heat flows from a warm object to a cooler object, relatively cooler object. So as long as the coffee is warmer than the outside environment, it's going to continue to lose heat and the temperature is going to drop. But as the temperature is dropping, if eventually the coffee is the same temperature as it is outside, then it's not going to be losing heat anymore. It's not going to keep getting colder, right? If the temperature outside is 60 degrees, the coffee's not going to get to 60 degrees and then continue to lose heat. It's not going to keep going down to 50 and then 40 and then 30 degrees. It's not going to freeze, sitting by itself on the picnic table. It's only going to lose heat as long as it's warmer than the environment. So what we could do to find the temperature outside is we could set the coffee outside for a really long time. Set your coffee outside for 1,000 minutes, and then eventually your coffee should just reach the outdoor temperature and stay that way. So in my little heat transfer model, if I were to type in some really large value for lowercase t, we would get 45 plus 140 times e to the power negative 0.05 times 1,000. And this is 45 plus 140 times e to the power negative 50. And when we were graphing exponential functions, you remember on the right side, e to the x shoots up really fast, super steep. But on the left side, it just flattens out. It gets closer and closer and closer to 0. And the graph just gets really a flat line. That's basically 0. So when I've got e to the negative 50, e to a really large negative number is practically 0. So I've got 45 plus 140 times something that's practically 0. That's 45 plus something that's practically 0. This is just 45 degrees Fahrenheit. And that means the temperature outside must have been 45 degrees Fahrenheit, if this is the model we're working with. So after a lot of time has passed, this temperature is just going to get closer and closer and closer to 45 degrees Fahrenheit until it's practically 45 degrees Fahrenheit. That's the temperature outside.
So would we use 1,000 minutes on all of them?
You could, or you could use 2,000 or 3,000 or 4,000. This doesn't matter. It's got to be a big number. You get the same answer. So I put this formula on the top of your homework, and honestly, I don't think you need to know this, but if you were taking a physics class, this is called Newton's law of heating and cooling. In this case, we were cooling down a hot object, so you might call it Newton's law of cooling. And what this says is that the temperature of the object we care about minus the ambient temperature, that just means the temperature of the surroundings, divided by the initial temperature of the warm object we care about minus the ambient temperature. This ratio is equal to e to the power negative kt. K is a constant where this number just depends on the situation. What I mean by that is air might have a K value of negative 0.05, but water might have a really large K value, right? Because you know a warm object cools down in water a lot faster than it would cool down in air. If you're trying to cool down a hot pan that you just took off the stove, it cools down faster if you submerge it in your kitchen sink water, right? Versus if you just wave it around in the air. So it depends on the situation. So in the previous question, when we were working that exercise, we said, well, the outside temperature was 45 degrees. The initial temperature of the coffee was 185 degrees. And if I rearrange this, well then 185 minus 45 was 140, so maybe I start by multiplying both sides by 140, and then I add 45 to both sides of my equation. And that's how you get a formula for temperature that looks like what we just had in the previous question. We'll do another one really quick. A pizza is placed in the oven. The temperature of the pizza is going to be capital T, and the number of minutes that have passed is going to be lowercase t. What was the temperature of the pizza when it was first placed into the oven? Yeah. If it was just barely placed in the oven, then 0 minutes have passed. And e to the power 0 is just 1, and 400 minus 330 is 70. So The temperature of the pizza was basically room temperature when you first put it into the oven. What was the temperature of the pizza after 10 minutes have passed? Okay. 236 degrees Fahrenheit, so it's warming up after 10 minutes. What was the temperature in the oven? Yeah. The same thing, if I plugged in some huge number for t, then the exponential term is going to be practically 0. Because e raised to a large negative number is practically 0. And so the temperature in the oven was 400 degrees Fahrenheit. So again, Newton's law of heating and cooling, they're the same equation. Heat transfer is kind of a symmetric thing where the heat always goes from a warm object to a cold object. It doesn't really matter whether the warm object is the ambient surroundings or the warm object is the object itself. We still take the temperature of your object minus the ambient temperature divided by the initial temperature minus the ambient temperature, set it equal to e to the negative kt. And in this case, my ambient temperature was 400 degrees, right? This time the oven was the ambient surroundings. The initial temperature of the pizza was 70 degrees. And so if you were going to rearrange this equation to solve for temperature, then you would get a formula that looks like, well, 70 minus 400 is negative 330. And then I would add 400 to both sides, and I would get a formula that looks like that, which is what you started off with in the previous question. Before I move on, is there any questions about like exercise 1 and 2? Does that make sense? Okay. So then moving on, we're switching from physics to biology. If you've ever heard of an invasive species, when biologists talk about an invasive species, they mean like a species that has never historically been in a particular ecosystem that gets artificially introduced into an ecosystem where it can outcompete all the other species and it does really well. Like one example is in the Florida Everglades, there have never been Burmese pythons. Burmese pythons are from Burma. And so when pet owners bought Burmese pythons to keep as a pet at home and then decided they didn't want them anymore, and they go and release them into the Florida Everglades, these, foreign pythons can easily outcompete all the other species in the Everglades, and there's ample food supply for them, and they just reproduce really quickly. The rate at which the population is growing is proportional to the population size at any time. Because to make a new python, you just need a male python and a female python. And so the number of current today, modern day male and female python, that's the rate at which you're producing new pythons. It's the rate at which the python population is growing. So when this happens, you get exponential growth. And this is the exponential growth formula. The y on the left side of the equation, that's the current population. The y with the subscript 0 here, that's the initial population. And R is an exponential growth rate, and T is the amount of time that's passed. So in this example, we're asking how many pythons were there 8 years ago? You guys are way ahead of it. Way ahead of me anyways. So we know from my problem that the growth rate is 0.2. We know that the current population is 40,000. We know 8 years have passed, and we're trying to find what was the initial population. So I write 40,000 equals my initial population that I'm trying to find times e to the power 0.2 times 8. So in my calculator, I could type in 40,000 divided by e raised to the power, open parentheses, and then 0.2 times 8. And some of you have already done this, and you said it was $8,075. 75, okay. Yeah, so that seems about right. So if today you count 40,000, that means 8 years ago, there's probably only 8,000 of them. They're just reproducing really fast. The other part of this question says how long, and that means I'm looking for t. And how long does it take the population to double? Well, double, that means y is equal to 2 times y0. So using the same equation, I would write y is equal to y0 times e to the power r t. I'm actually trying to find t. So I divide both sides by y0. And I'm trying to solve for little lowercase t. How do I solve for t? Yep. I'm trying to get rid of an exponent base e. And so I would want to use the logarithm base e. The logarithm base e is the natural log. And that would be natural log of 2 equals 0.2t. And that means t is equal to the natural log of 2 divided by 0.2. And what is that? 3.46 or 47, however you round it. Years, in this case. So every 3.5 years, you get twice as many pythons. And the population would keep growing like that until they ran out of food, or until you introduced a predator that would eat the pythons. But at least initially, when you introduce an invasive species, it grows exponentially, and so it would double every so many years. Questions about this one? Okay, similar question, slightly different. Says that a biologist has a petri dish, and a petri dish is just a little glass dish where you put in a kind of a jelly, kind of a gelatin type solution with a lot of sugar and a lot of protein so that the bacteria can eat it and grow really fast. And so if you have a petri dish and you add 100 bacteria to it, and maybe you know from previous experiments that this doubles every 20 minutes, what would be the growth rate? Doubling means, just like before, this y is the same thing as twice the initial population. And so let's assume that we're waiting for this to double, and it doubles every 20 minutes. So then I set up my equation 2y0 equals y0 times e raised to the power 20r. I'm looking for r. I want to find what my growth rate is. How do I solve for r? Yeah, I want to get rid of an exponent base e, so I have to use the logarithm base e. And the logarithm base e is the natural logarithm. So I write ln of 2 equals 20r. And that means r is natural log of 2 divided by 20, which is 0.03? 34? When you write down your answers, go ahead and use 3 significant figures. And so, is it 340 or is it 34 or something else? 346. Okay, so the way I would write my answer is 0.0346. We don't count zeros as significant figures, so I would start counting significant figures when I get to the 3. I would write 346, and that would be the answer. That's my growth rate. The next question asks, how much time will pass? And so I'm looking for a t, for how much time, before there are 1 million bacteria. And I know from the statement just above this, it said that the biologist was going to seed the petri dish with 100. That means that's the initial amount, it's the initial population. So I'm going to use the same formula and write 1 million, that's a 1 with 6 zeros, is equal to 100 times e to the power rt. I'm looking for t, and r, we just found in the previous question, r is 0.0346 times t. Okay, so divide both sides by 100. And now I should Yep. If I want to get rid of the exponent base e, then I take the natural log of both sides. And that means t is equal to the natural logarithm of 10,000 divided by 0.0346, which is okay. So 266, that's 3 significant figures, and that is in minutes, I believe. Because my half-life that we started from was given in minutes. It said 20 minutes. So this lowercase t is now in minutes. 266 minutes, that's like, I don't know, 4.5 hours? So if I want to go from 100 bacteria to 1 million bacteria, and they have enough food and enough whatever else they need to continue to reproduce, then I should have 1 million bacteria in 4.5 hours. So you just write down this formula, the exponential growth formula, and figure out what the problem's telling you, figure out what the problem's asking from you, rearrange it. If you're solving for a variable that's in the exponent, you just take the natural log of both sides, kind of like we've been doing for the past couple weeks. Any questions? All right. Let's talk about half-lives. Half-life. The word half-life means the amount of time it takes for half of a substance to go away. If I were to drink a coffee, that's consuming about 200 milligrams of caffeine. Well, the half-life of caffeine is 5 hours. So 5 hours later, my bloodstream would only contain about 100 milligrams of caffeine. And 5 hours after that, my bloodstream would only contain about 50 milligrams of caffeine. And 5 hours after that, I've only got 25 milligrams of caffeine. And 5 hours after that, it would be 12 milligrams of caffeine, and so on. So every 5 hours, the amount of caffeine that I still have is going down by half. This is called exponential decay, and you'll notice it's exactly the same formula as we had for exponential growth, only now R is a negative growth rate if it's decaying. So R is negative for decay. Anyways, exercise number 5 says Alice drank a coffee containing 200 milligrams of caffeine at 8 a.m. The half-life of caffeine is 5 hours. What is the decay rate? What's this little lowercase r? So y equals y0 times e to the power rt. If I'm talking about the half-life, then I'm telling us how much time does it take for the current amount to be 1/2 of the initial amount. So back here, instead of writing y, I'm going to write 1/2 of the initial amount equals the initial amount times e to the power r. And then the little t here is the amount of time it takes to half the amount, and that was 5 hours. So I divide both sides by y0, and 1/2 equals e raised to the power 5r. If I want to solve for r, what do I have to do? I have to take the natural log of both sides. So we see why the natural log comes in handy. In the end, r is equal to the natural log of 0.5, or 1/2, divided by 5. And that is 0.138? Yeah, there you go. That's my decay rate. If I have a half-life of 5 hours, then I would write r equals negative 0.138. Next question. What is the amount of caffeine still remaining at 10 p.m.? So this time I'm looking for the current amount. I'm looking for y. The initial amount is 200 milligrams times e to the power r. Oh, I know r. I just found it in the previous question, negative 0.138. And then t is 14 hours. Yeah. So between 8 a.m. and 10 p.m., 14 hours have passed. And so this is something you can put in your calculator. You type in 200 times e raised to the power, open parentheses, negative 0.138 times 14, close parentheses. You said 20? 28.97. Okay, that's funny. In my previous class, they got a different number, so they did it wrong, because I see multiple students here have gotten the same thing. So I'm sure this is right. I'm sure my last class was wrong. Anyways, this is milligrams. That's how many milligrams of caffeine are still left at 10 p.m. So it's about, 15% of what she originally drank in the morning. The last question says, how much time must pass, so I'm looking for T, if I want the amount of caffeine to be reduced to 15 milligrams. And so writing down my equation, y equals y naught times e to the power rt, y is 15, y naught is 200, e to the power negative 0.138, and this time I'm trying to find how much time has passed. So I divide both sides by 200, and then to get rid of the e, I need to use the natural logarithm. And if you rearrange this equation correctly, this is going to be the natural logarithm of 15 divided by 200 divided by negative 0.138, and you get cool. So if you drink your coffee and you only want 15 milligrams of caffeine, well, then you just have to be patient and wait 18.77 hours. A little hint for using your calculator. Your TI-30X2S, it has two different buttons, one for minus and one for negative. If you accidentally put the minus sign down here, it'll give you an error. So you have to be careful and use the negative sign right here if you want the answer. Yeah. Okay, any questions about this type of question? No? Once again, the hint is when you're searching for a variable in your exponent, then you have to take the natural log of both sides. Okay, last question for today. Speaking of half-lives, this is a concept from chemistry. In chemistry, you learn certain types of atoms are called isotopes when they have too many neutrons. If your atom just has too many neutrons in the nucleus, it's not stable. It's going to decay eventually. And how unstable it is determines how long it can last before it decays into a different type of atom. So for example, carbon-14 is an isotope. It's an unstable type of carbon. And we say it's unstable because every 5,700 years, half of the carbon-14 decays into nitrogen-14. Which is just a more stable type of atom. Carbon-14 is not super duper common. The only process that naturally creates carbon-14 is in the very upper atmosphere of Earth, where the high energy radiation from the sun hits carbon dioxide molecules. Then that high energy radiation can turn the carbon-12 or carbon-13 and the carbon dioxide molecules into carbon-14. But the process is super slow, and the whole time carbon-14 is still decaying at a particular rate. And so it doesn't build up very much. It's still a very, very, very tiny concentration in the atmosphere. This is a tiny concentration. I can tell this is a tiny number because it's 10 to the negative 12 power. 10 to the negative 12 is like 1 divided by 10 to the 12 power, which is 1 divided by a trillion. It's 1 in a trillion, or 1.25 in a trillion parts. Very tiny concentration of carbon-14. So That's what it is in the atmosphere. And if you are an archaeologist, one of your jobs as an archaeologist is to go around looking for old stuff, right? You go tramp around in places that aren't very highly, trafficked, places where people don't normally go, and you're looking for, I don't know, fossils and old tools and anything you can find of days long past. So, true story, archaeologists are messing around in the Czech Republic and they find a small village that seems like it's an early human settlement. It seems like hunter-gatherer days, right? Like before the agricultural revolution. Clearly they're humans because they're using tools and stuff and they're building tents. But they're not building subways and power stations and stuff. So you come across this, and they've got mammoth bones that have been kind of collected and used for tools or whatever. And you want to know, as an archaeologist, how old is this, right? Like, if you're an archaeologist, you want to know how long ago was this tribe of humans tramping around, doing their thing. Well, here's what you would do. You would take a little scoop of one of the mammoth bones, and you take it back to any modern day lab that has fancy equipment, whatever, and you ask the chemists, please tell me, what is the concentration of carbon-14 among the total carbon in this organic material? And they'll run their fancy machines and they tell you, the total concentration of carbon-14 among the total carbon atoms in this material is a super tiny number, it's 4.7 blah blah blah, times 10 to the negative 14. So very, very, very small number. And how could you answer the question, how old is the mammoth bone? Well, you would write down your equation, y equals y0 times e to the power rt. This is the current concentration. This is y, 4.76918 times 10 to the power negative 14. And this is your initial concentration, 1.25 times 10 to the negative 12 times e to the power rt. What is little lowercase r, right? I'm trying to find t. I don't even know what that is right away. I'm trying to find t eventually. But I do need to know what is r if I'm about to solve this equation for t. I don't know what r is. My question didn't really tell me what r is. But if I know that the half-life is 5,700 years, that means the final concentration is half of the initial concentration after a time of 5,700 years have passed. So then I could write down this formula, and I'll trade out the y for 1/2 y naught. Divide both sides by y naught. T is 5,700. And so this r is going to be the natural log of 1/2 divided by 5,700. And so somebody with your calculator, tell me, what is little lowercase r to 3 significant figures? Should be negative 0.000. 121? Is that right? Okay. So r is negative 0.000121. It's a really small number because the half-life is 5,700 years. It has a long half-life. But r is negative 0.000121. Okay. So one thing I might think to do is say I've got 10 to the negative 14 on this side and 10 to the negative 12 on this side. Let me go ahead and take both sides of the equation and multiply by 10 to the 12th power. And on the right side of the equation, I've got 10 to the 12th power times 10 to the negative 12th power. So if I add the exponents, then negative 12 plus positive 12 is 0, and 10 to the 0 power is 1. And so these cancel each other out. On the right side, I've got 10 to the negative 14 times 10 to the 12. And I just add the exponents. Negative 14 plus 12 is negative 2. I'm not going to rewrite that number. I'm trying to conserve my pencil lead. So 10 to the negative 12, that means 1 divided by 10 to the 2 power, and that's 1 divided by 100. And if I divide by 100, that just means I move the decimal place over. And so I would say this is 0.04766918 divided by 1.25. And that's equal to e to the power negative 0.000121 t. Now, let's take the natural logarithm of both sides and then divide both sides by r, and we'll have t equals the natural log of 0.04766918 divided by 1.25. Close parentheses, divided by negative 0.000121. Okay. So, yeah, about 27,000 years old. And this is what people do. This is called radiocarbon dating. And if you're an archaeologist studying this kind of thing, then this is exactly the kind of math they're using. Especially if you're opening up a history textbook and you're just reading it from cover to cover. Chapter 1 is probably about prehistory, and they talk about all these dates like, we think the agricultural revolution started between 9,000 and 10,000 years ago in the Indus River Valley. Cool, how the heck do they know that, right? Like nobody was saying exactly when they started farming, but why do they think that? Well, it's because they started discovering farming tools that were made with wood, and wood has carbon. Let me ask you guys another question before you leave. I told you that the concentration of carbon-14 in the atmosphere is this number. Why would I use that as the initial carbon-14 concentration in the mammoth bone? Why would the mammoth bone carbon be the same as the current day atmosphere carbon? So the answer is, we would expect the carbon-14 concentration in our atmosphere to be roughly the same, because the Earth has always been about the same distance from the sun, so we get the same amount of high energy radiation, and the carbon-14 is generated at the same rate, and carbon-14 always decays at the same rate. So we expect the concentration to be the same. Where did the carbon in the mammoth bone come from?
It breathes.
Not when it breathes, but you're on the right track. It comes from when it eats. The mammoth is going around eating stuff, right? It eats plants and leaves and whatever. Okay, so if the mammoth is what do mammoths even eat anyways? Are they herbivores? Let's assume that we're talking about a cow, right? Cows eat grass and they eat corn and they eat vegetables, right? So if this were a cow or a mammoth and it's going around eating grass, then all of the carbon that makes up the mammoth comes from the food it eats, right? You are what you eat. Where does the grass get its carbon from? When it breathes. So plants inhale carbon dioxide and they exhale oxygen. And in the meantime, the carbon from the carbon dioxide goes into the plant. And the plant uses that carbon to build leaves and stems and roots and plant stuff, right? All that stuff is made out of carbon. So the plants are breathing in carbon dioxide from the atmosphere that has a certain percentage carbon-14. The plants then get eaten by animals, and that makes up the animals with a certain percentage of carbon-14. And then the deal is that when the animal dies, it quits eating. So that's the initial concentration of carbon-14 in the animal. So that's the moment it died, that's the moment it quit eating fresh carbon. And anyways, I think it's cool. I think it's crazy that anybody thought of this method for dating old stuff, but that's how it works.